This lesson is on the formal definition of a limit, sometimes called the epsilon delta definition. Fairly challenging to understand, but I'll try to help you with that. And we'll do that by looking at a function and try to establish what its limit will be. We know that if a function is continuous, the value of the function is the same as the value of the limit. So I'll start with the continuous function in my first example, and I'll show that it also works for a function that is not continuous if it has a limit. We are approaching C. Here is f of C of some function y equals f of x. So this is the point C f of C, but I'm going to also call that L for the limit. Okay. So what I want is I want the limit as x approaches C of f of x to equal L. So what am I going to do next? We're going to define this using epsilons and deltas. So here is our formal definition. Given any epsilon greater than 0, there exists delta greater than 0. So we're going to start with an epsilon greater than 0, and we're going to say from that epsilon we can define what delta is. So let's first focus on epsilon before we finish this definition. It's a small number. So we're going to add epsilon to L. So this high end would be L plus epsilon. And on the low end, that would be L minus epsilon. And what this does, it creates a ribbon of values. Okay. This is a range of values, a lowest range and a highest range. So from that epsilon, I'm going to create a delta. What is a delta? A delta is going to be a little bit less than C and a little bit more than C. So this point is C minus delta. And this point is C plus delta. And what are we saying about that? Well, we're saying there exists a delta greater than 0 such that if 0 is less than absolute x minus C, is less than delta. So that means I choose any number in that interval except for C, because C would give me 0. If I choose any number within that interval, all of the values of the function will be within that ribbon. If I choose any nice number in that interval other than the center, all of the values of the function have to be contained in that interval. So how do I write that in mathematics, in logic? If I choose a number in that interval between C minus delta and C plus delta, then the difference of the values of the function, like might be this f of x, 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 this f of x. The difference between the value fx and that L must be less than epsilon. So if I choose any number close enough to C, all of the values of the function will be close enough to L. So that's what that means. So let me go ahead and see if we can find a delta for a given epsilon. So let's take a look at f of x equals x squared. We're going to look at the limit as x approaches 2. So f of x equals x squared. I want to look at the limit as x approaches 2 of f of x, and that should equal limit as x approaches 2 of x squared, which should be 4. So in our example here, right, fine, f of x is x squared, c is 2, and L is 4. So given any epsilon we want to try to use. So for the sake of discussion, let me choose an epsilon of 0.05. Find the corresponding delta. Okay, so that means we're going to go up from 4 by 0.05, down from 4 by 0.05. So we'll do an exaggerated drawing here. So here's 4. We're going to go up 0.05, we're going to go down 0.05. So 4 plus epsilon, L plus epsilon is 4.05. L minus epsilon, 4 minus 0.05 would be 3.95. I want to choose a delta. We're approaching 2. So here's what I'm approaching. I'm approaching 2. I want to choose some delta. So this is 2 plus delta here and 2 minus delta here. So that all of the values of the functions, except perhaps at 2, are within that ribbon. So we draw out that ribbon. So going up to 2 plus delta, the answer, the value of the function has got to be beyond that part of the ribbon. The 2 plus delta has to be below that part of the ribbon. It's got to be contained within that. And everything in between has to be within that ribbon, except possibly at 2. What happens at 2 is irrelevant. It's just what happens near 2 that our issue is. So we want to find out what that corresponding delta is. So can I find some delta? Now, maybe if it's 1 part out of a million, obviously it's likely to work. We want to find maybe the largest possible delta or one of the largest possible deltas that we can use. That's our goal. So let's go to Desmos and let's see what we get. So pulling up Desmos, I have y equals x squared. And we are approaching 2, right? And we believe that that limit is 4. So we want to go up 0.05 and we want to go down 0.05. So y equals 4 plus 0.05 and y equals 4 minus 0.05. 3.95 to 4.05. And let's make those dotted lines. Dotted line in green maybe, and a dotted line in green. So I've got to choose numbers close enough to 2 so they stay in between those 2 dotted lines. It's hard to see what they are because those 2 dotted lines are so close to each other. But let's zoom this thing in if we can. And we'll keep zooming it in. So now all of these numbers are within that ribbon. So 2.0112, looks like 2.0125 gets me on the ribbon. So let's just go a little bit lower than that. So 2.0106, 0108. Maybe I can zoom it in again even. Whoops, zoomed in too much. Okay. 2.0114. So it looks like 2.01 for sure is going to be okay at the high end. How about on the low end? If I go below, is 1.99 good? Yeah, it looks like it is. So it looks like 1.99 is within the ribbon. it looks like 2.01 is within the ribbon. So a delta that will work here would be 0.01, 2 minus 0.01, 1.99, 2 plus 0.01, 2.01. So a corresponding delta that I could use to stay within that ribbon is if epsilon equals 0.05, I can let delta equal 0.01, and I have shown on the graph I have shown what I have shown if absolute, well, if 0 is less than absolute x minus 2 is less than delta, or 0.001, then f of x squared minus L, x squared minus 4 is less than epsilon. That's what I've shown. But I want to recognize that I can use any epsilon. There's nothing magical about 0.05. So let's do this again with a smaller epsilon. And we'll have to zoom it in even tighter to see what is our value delta going to be to stay within that window. So we'll use the same example, f of x is x squared, and the limit as x approaches 2 of f of x equals the limit as x approaches 2 of x squared equals 4. So good enough in our example, of course, f of x is x squared. L is 4, and C is 2. So the first time I did this, I chose epsilon as 0.05. This time, let me choose epsilon equals 0.001. Again, for any epsilon that I choose, I should be able to choose a delta small enough so that all of the values in that interval, all of their function values are within that ribbon. So let's draw our picture so we can visualize this. Here's 4, or L. We're going to add epsilon, so that'll be 4.001 here. And L minus epsilon, 3.999 here. That creates a ribbon. Then I'm going to go to 2 here. And I need a 2 plus delta and a 2 minus delta, so that all of the values of the function, except possibly a 2, are within that window. Maybe this one lands here. This is an increasing function, so I know it's going up. Maybe that one lands there. So how small does delta have to be so that all of those values of the function stay within that ribbon again, except possibly at 2? What happens at 2 isn't important. So let's go back to Desmos one more time. And this time I need 4.001 and 3.999, or 4 minus 0.001. So really, really close together. So what do I have to do? How much do I have to zoom in to be able to see enough play within that ribbon? Okay, maybe this is pretty good. So how high do I go here? 0.0002 looks pretty good. How about minus? It'd be 1.9998. Is that within the range? It looks like it is. I'd like to have a little bit more accuracy though in there. So let's see what we get for delta is 0.0002. Is what we think based on what we have here. But let's try it. So our hypothesis from our picture delta is 0.0002. So if I go a little bit to the left, 2 minus delta is 1.9998. 2 plus delta is 2.0002. So what is the value of the function, right? So what is f of 1.9998? Is that within the interval? Is that within the window? What is f of 1.9998? Let's go to the graphing calculator and take a look. So that's x squared, right? So 1.9998 squared gives me how much? 3.9992. That's beyond 3.999. So that's within the window. So that's good. So within the window. How about f of 2.0002? You need that to be within the window, means it's got to be less than 4.001. So 2.0002 squared. Is that less than 4.001? 4.0008. Yep. Which is less than 4.001. And we know that this function is increasing, so everything in between is going to be within those two values. So what does our formal rule tell us, right? For any epsilon greater than 0, we've tried two of them. We tried 0.05, we tried 0.001. This is not a proof. This is just helping us understand what the directions say. For any epsilon greater than 0, we have to find some delta. Notice that delta changes depending on the epsilon. There exists delta greater than 0. So in this case, epsilon was 0.001 and our delta was 0.0002. There exists a delta greater than 0 such that if you pick any number in that interval except for the middle, if for any number x minus c, x in that interval, x minus c, so it's got to be close. X minus c is less than delta means it's close, other than, of course, c itself. For any x in that interval other than c, then absolute f of x minus L has got to be less than epsilon. We've shown it for two epsilons. Again, not a proof. We'll do a proof of a similar problem shortly, but that's our basic idea. All right, let's take a look at one more problem where we are given the epsilon and we have to find a delta. So, and this time, maybe I will work with a problem that is not continuous. So how about the limit as x approaches 3 of x squared minus 9 over x minus 3. And I could even do something like this, rather. Let's even change it a little bit. Let's let f of x equal x squared minus 9 over x minus 3 if x doesn't equal 3, but it equals 1 if x does equal 3. So we'll make it a piecewise function. That's even better. So let's take a look at that graph. So small change on that. So we'll scratch that. We'll take a look at the limit as x approaches 3. And let's look at our graph. What does that look like? What is that telling us? And then we'll pick an epsilon, and then we will find a corresponding delta. So going to Desmos, we have y equals x squared minus 9 divided by x minus 3. But that's only true if x doesn't equal 3. and go to the regular graph. Well, we know it can't be, x cannot be 3. And then at 3, we're going to put 1. So we have a hole at this point here because it doesn't equal that. So we'll put a hole at 3, 6. Make everything red. So here's our graph, and it does satisfy the vertical line test because the vertical line here only hits 1 point. So we want to pick an epsilon. What do we think the limit is, first off? The limit as x approaches 3. As I get closer and closer to 3, the value of the function gets closer and closer to 6. Removable discontinuity. So that limit as x approaches 3 of f of x equals 6. So I've got to choose an epsilon. Maybe this time I will choose the epsilon to equal, choose epsilon to equal 0.05, which means I'm going to go, from our picture, I'm going to go 6 plus 0.05, 6 minus 0.05. We believe the limit is 6. We create a ribbon, 6 plus 0.05, so that's 6.05. 6 minus 0.05, that would be 5.95. And that creates a ribbon. And I've got to choose a delta close enough to 3, a little bit to the left and a little bit to the right. 3 minus delta, 3 plus delta. So it always stays within that ribbon, stays within the ribbon. This will also be increasing, stays within the ribbon. What happens at 3 doesn't matter. We know what happens at 3 is it's 1. But what happens at 3 is irrelevant to this discussion. What happens near 3 is what we're interested in. So you're right. F of 3 will not be within that ribbon. That's okay. So 5.95 to 6.05, this interval does not contain f of 3. But that's okay. That's not my concern, because what we say is, we say given epsilon greater than 0, given any epsilon greater than 0, there exists delta greater than 0 such that if 0, that's the key, is less than x minus c, is less than delta. So what happens at c, what happens at 3 here doesn't matter. Then absolute f of x minus L is less than epsilon. Okay, so we want to find out what the delta will be so that it stays within that ribbon of 5.95 to 6.05. So let's do that. Go back to Desmos. And we need y equals 6.05, which I'll make green and dotted. And then I need y equals 5.95, which I will make green and dotted. And I need to zoom in close enough so that all of the values of the function are within those 2 dotted lines. Now notice this one will not be. And like I said, what happens at 3 is irrelevant. What happens near 3 is what matters. So I'm going to zoom in on this. It's probably pretty good. So I need to recognize it's 3 plus something, 3 plus 042. 05 looks like it's landing. So I don't know, I'm going to go 3.04. So if I go to the left, how about 2.96? Looks like that's in the interval. So 2.96 to 3.04, that would give me a delta of 0.04. So here, if I let delta, if epsilon equals 0.05, the delta I would have to choose, the delta is 0.04, and all of the numbers in that interval now, from 2.96 notice its function value is in that ribbon, to 3.04, its function value is in that ribbon. Now this one is not, right? Because that one is, it's not undefined, it's actually -1. But again, what happens at that point doesn't matter. But we have found for all of the points near 3, we're able to choose a delta small enough so that all of the points near 3 have function values that are close enough to L within that epsilon window. That's what the formal definition of the limit means. That is what the epsilon delta definition is.